4. Fluid Kinematic. Welcome to Chapter 4, Fluid Kinematic. In fluid mechanics, it's crucial to understand how fluids move before we even worry about forces. Kinematics focuses only on motion, how fast fluid particles go, where they travel, and how their flow patterns evolve without worrying about what causes the motion. This chapter is like learning the dance of the fluid, paying attention to its pathlines, streamlines, and streaklines. Think of it like observing cars in traffic from a helicopter. We don't care who's driving or why they're rushing, we just want to see how they move. Mastering this will help you interpret flow behaviors in pipes, rivers, and even aircraft design. Let's dive in.
1. Lagrangian and Eulerian descriptions. Fluid kinematics is all about describing how fluids move without caring about the forces behind that movement. There are two simple ways to do this. The first is the Lagrangian approach. Think of it like following a car with a GPS tracker. You track one particle and see where it goes. The second is the Eulerian approach. This time, you stay in one place, like standing by the roadside, and watch cars pass by. Instead of tracking particles, you monitor what's happening at a fixed spot. When we use the Eulerian method, properties like velocity, acceleration, and pressure depend on both location and time. The interesting part is how these two views are connected by something called the material derivative, which basically allows us to translate between moving with the flow and standing still and observing.
2. Flow patterns and flow visualization. When studying fluid flow, we can describe it by tracking how the fluid moves. There are 4 common ways. First, streamlines show the direction of the flow at one instant, like drawing arrows that follow the wind. Second, pathlines track a particle's actual journey, like watching a leaf floating down a river. Third, streaklines show all particles that pass through a point, similar to smoke trails from a chimney. Lastly, timelines are when we release a line of dye and see how it stretches with time. To see these in real life, we can use smoke or dye for streaklines, hydrogen bubbles for timelines, or advanced tools like shadowgraphy and computer plots. The goal is simple: make invisible fluid motion visible.
Number 3. Velocity and acceleration fields. When we describe fluid flow, velocity is our starting point. A velocity field tells us how fast the fluid is moving and in which direction at every single point. But flow isn't always constant. It changes over time and space, which brings in acceleration. Acceleration explains how the velocity varies, and it has 2 phases. First, local acceleration happens when the flow changes over time, like when you suddenly turn on a faucet. Second, convective acceleration happens because fluid moves from place to place, like a car accelerating when going downhill. Together, these help us understand velocity profiles, which are like speed maps of the flow under different conditions. Understanding these fields gives us a full picture of how fluid behaves in motion.
4. Kinematic properties of fluid motion. When fluid moves, it doesn't just drift in one way. It has 4 basic types of motion. First, translation, where the fluid simply moves forward, like a boat on calm water. Second, rotation, where fluid particles spin around, like a spinning coin. Third, linear strain rate. This happens when the fluid stretches or compresses, similar to pulling or squeezing a rubber band. Fourth, shear strain rate, where the shape of the fluid changes because some parts move faster than others, like smearing butter on bread. To measure how much a fluid rotates, we use vorticity. When it's 0, the flow is smooth and irrotational, but when it's non-zero, it means the flow is swirling or rotating. These 4 properties help us understand not just where the fluid goes, but how it behaves along the way.
5. Reynolds Transport Theorem, RTT. Imagine you want to track how mass, momentum, or energy changes in a flowing fluid. Doing this directly for every moving particle is complicated. That's where the Reynolds transport theorem comes in. It transforms system equations into something much easier using a fixed control volume. The formula might look scary, but it's just saying the total change equals the change inside the control volume plus the flow across the boundary. Each term has a job. B cis tracks the total amount, B focuses on value per unit mass, rho is density, V is velocity, and N points outward from the control surface. RTT makes it possible to apply conservation laws in practical problems, like how much fuel enters an engine or how much water flows through a dam.
6. Summary. Let's wrap it up with a quick recap. Kinematics helps us describe how fluids move, without worrying about what causes the movement. Between Eulerian and Lagrangian views, Eulerian is more common since it focuses on what's happening at a point, making it easier to map flows. We've seen 4 key flow patterns: streamlines, pathlines, streaklines, and timelines. Each one shows us different aspects of fluid movement. Velocity and acceleration are broken into local and convective parts, helping us track how speed changes. Strain rate and vorticity tell us how fluids stretch, deform, and spin. And finally, Reynolds' transport theorem lets us switch between moving systems and fixed volumes, which is crucial for solving mass, momentum, and energy problems. These tools give you a solid foundation to understand fluid flows in real life.